Okay, those design aids are very handy, very nice. They save a lot of time during your solutions, right? What are those design aids? It's simply things that are repeated so much. They figured out why not just put it in a table and give it to the designer, and the designer just goes through the vertical and horizontal choices and pick the number. Let's go over them. So, for example, this one, A1, and A1 is not that much used. A2 will be used more. It tells you the diameter of the bar, and then for every designated bar, what is the diameter and what is the cross-sectional area. Simple? Very simple. So for every one, you don't have to plug in pi d squared over 4 and get the area. So the area is given right away. But what is even nicer is A2. Let's go over A2. Here's A2. What A2 is giving you is for every bar, if I'm using one of this bar, this is the area. 2 of this bar, this is the area. 3 of this bar, this is the area. So right away, if I tell you I need 3, 5, 22, what do? You go to 22. You go to 3, down. You go to 22. This here is my AS. So right away, my AS equals 1161 millimeters squared. Simple? Very, very handy. You don't have to use the calculator. Once I give you a steel intention equals to this, go to table A2 and pull it out right away. In every exam, table A2 will be given. Okay? So you just keep checking things on the table. What table A3 is giving you, and this is more related to slabs, is it gives you for every bar at which spacing what's your AS. In other words, this is my section, right? Because the slab comes in a 1 meter width section, right? So always the slab width equals 1 meter. So how many bars do I have in 1 meter? I will not tell you. I will say, or how it's designated, I will say for example, phi 19 at 200 millimeters. Is the spacing between the bars. So between each bar and the next bar is 200. Then I go to the 200 and I go to phi 19 and then I find this would be my AS. Okay? So this when it comes to slabs, depending on your spacing, this is how it goes. Okay, so area 3 is basically for the slabs. I'm sorry, table A3. Now, table A4, that's very nice. Remember when I said to calculate the row minimum? How do we calculate the row minimum? It is the larger of two equations. Those are the two equations. This equation and this equation. Now, this table saves a lot of times doing the calculation. So, you get in with any F yield of those. Right? The most commonly used in the Middle East is the 420, right? And then, which F prime C do you have? For example, I have the 28 F prime C. Then all of those numbers are given. What are those numbers? These two numbers are row minimum. You compare them together to take the larger, right? And then we have two nice numbers. This is the row of 0.004 strain and the row of 0.005 strain. Okay? We'll get to know why do we need to use them. But the nice thing also is your beta 1. Remember what beta 1 is? Here's beta 1. Tamam? So if you see F prime C right away, so from table A4, beta 1 equals this right away. Okay? Okay, so this is table A4. Going to the next table up is table A5A. A5A and A5B, it talks about something called the R value. Now, this R value will be explained in part 5, once we get into part 5. It is very nice to use R value when we are doing the design, rather than using the big equations that we had. So, simply, how to use this? Go to whichever F yield you have, go with the row that you have, right? And then pick through, for example, I have an amount of steel. I get my row and then go in and then find this is R. Okay? This is very simple to use. Now you will be confused a little bit now, understanding what R is. But once we get into the design in part 5, R is a very, very useful factor. We call it the flexural resistance factor, and it's calculated in megapascal. We just convert a whole lot of factors or variables and plug R instead. What does it depend on? It depends on F yield, F prime C, and the amount of steel divided by BD. Okay. Okay, and then you go for the B is continuing with the values of rho, and at one point rho disappears. So this is table A5. Going to table A6, we will not use the crack sections. So the table A6 is not part of your calculation. A7 and A8 are very handy, very nice. Says that this is the maximum number of bars as a single layer in a beam stem. What does that mean? Remember CS minimum? When I told you to calculate CS and then compare it to CS minimum? This table does it for you. Which means you can get in, I will give you, for example, a section that looks like this, and you have those bars. Like say, for example, this is phi, I'll make it big, phi 32. And your stem width, which is B, is equal to 250. You understand? I'm giving you 3 phi 32 and a 250. You got it? And I told you check the spacing requirement, or this is the first step you need to look at. Then you will go and do CS and calculate CS minimum, right? And then you will go over the calculations. This table will tell you for a stem width of 250, here's the 250, right? For a phi 32, your maximum is 2 bars. Then you cannot do this. You got the idea? For a phi 32 here, your maximum is 2 bars. What's the difference between the top and the bottom? It is the size of your aggregate. Somebody did ask me this question back in when I was describing. He said, is there any requirements for the aggregate? This table takes care of the aggregate size as well. Yes. Or be on the conservative side. Okay? So this here tells you that your maximum number, then you cannot do this. In this case, what do? You either change the bar diameter or make a new line. Right? So in this case, try to use 4 bars instead of 2 bars. And then get an equivalent AS. An equivalent AS could be used. You don't have to use the phi 32. You could go with the phi 25 muscle. The next one up is the minimum number of bars. The minimum number of bars, right? What does that mean? It means, remember when I talked about S allowable, I did not talk about it yet. It's in part 5. It's like the slide 5 or 6. What happens here is if you have big distance between your bars, this will allow for crack to happen. So to avoid this, you have a minimum amount of bars within a stem. So the minimum amount of bars, it could go down to 1. You could put one bar. That's fine. In some joists like this, they get 1 bar. This is fine. This happens especially in ribbed slabs. You could have 1 bar down at the bottom because they have a lot of ribs next to each other. But generally speaking, for example, I have 300. I cannot put 1 bar phi 16. This is not allowed. A minimum of 2 is needed. Do you understand? And you keep going with this. Now, what's the difference between the top and the bottom? The difference is the clear cover. The difference is the clear cover. Because the equation that uses this, we'll see this equation together in part 5, uses the clear cover as part of the criteria to find how big of a distance the bars should be at. Okay? Now, the nice thing about this table, table A9, what does A9 do? It calculates phi mn for you. Can you imagine what's nicer than this? But it's only for slabs, not for beams. Right? Yeah, what are we doing here? Now, for a slab with a 1 meter width, because remember the beam has so many variables, right? But slab, one of the variables is gone, which is all slabs have a width of 1 meter, right? Because you're designing 1 meter per slab. And for an F yield equals 420, and you go for an effective depth that is variable. You have limitations on slabs is very good. Like you don't have very thick slabs, but you could have a very thick beam. So the slab goes between 75 all the way to 300, and those are F prime C's, and those are rows within each F prime C. It gives you phi mn right away. Okay, what is the last one? Tension development in the bar, and this is not part of your development in the compression. This is not also part of this. So forget those two until we get to the detailing chapters, and that concludes this this design 8. Thank you.